Hi, so this is the fourth part of the series on Python for astronomy. Uh, in this part, we will be working on color magnitude diagram, which is an essential tool for an astronomer. So we will be using some of the libraries which you learned earlier, particularly in the first two sessions where I discussed about NumPy and Matplotlib, because I want to visualize stuff in this. We won't be using AstroPy for this session, but we will be using NumPy and Matplotlib. So the idea of using color magnitude, like the color magnitude diagram, essentially is a tool for an astronomer because it gives you an idea of various properties of a particular star cluster or a particular galaxy. Like we will see that using this we can find a distance to a particular star cluster, or we can find the age of a star cluster, and so on. I'll start with the theory of this so that you'll understand. Even if you don't have much background about this stuff, you can just catch up on this. I'll just briefly go through that, and then we'll use some of the data which will be present in the GitHub repository, and I'll also teach you how to, do get data by your own, like generating data and so on later. But first we'll focus on the data which are available to us, which is available in the repository. We can use that to play around with it, and then you can venture into even your own data, even data from your own telescope. So HR diagram, or the Hertzsprung-Russell diagram, is essentially the same as color magnitude diagram. Equivalent, they are equivalent to each other, but there are some slight differences. First of all, HR diagram is essentially like a scatter plot. Just zoom out a bit. So you can see that this is just a scatter plot of the luminosity, which is on the y-axis, and the surface temperature on the x-axis. These diagrams were actually developed independently by Hertzsprung and Norris Russell, and it's a great step towards understanding like the idea of stellar evolution. So you can actually see some labels like, main sequence, supergiants, giants, white dwarfs. I'm sure you would have heard about this at some point. Like you can look for sun over here. The sun is right over here with some temperature around 5000 Kelvin, sorry, 6000 Kelvin, and then you have its luminosities, which is measured in solar units, so it will have one solar unit luminosity. So the sun is present in this particular line called as the main sequence line, which you can see most of the stars fall in this particular main sequence line, and there are these lines that jump out of the main sequence in this particular branch. They are the giants, and then there are supergiants. For example, you can identify this particular star called Betelgeuse. It was in news recently. And then you have these objects called the white dwarfs. So to understand them, first of all, let's let's actually learn about the luminosity and how it is dependent on the mass. So you can see that the most luminous stars are actually the massive stars. This is a property of stars, that the luminosity and mass, there is a dependence, and you can find the dependence. You'll see that the more massive a star is, the more luminous it is, and you can see this is around 60 solar mass, and it's covering around 10 power 6 solar luminosity unit. And you can also observe that going down, the luminosity decreases, also the mass decreases. Along the x-axis, it's the decreasing temperature. Just don't confuse with the way the axis is arranged. Like this is the increasing temperature side, and this is the decreasing temperature. So you can find the stars which are more massive and more luminous. Also, they are very hot at this point. These indicate really hot stars, these blue stars. Whereas on the right side, when you decrease the temperature, you get these red giants or red supergiants and these red stars, which are essentially, their temperatures are lower compared to the normal blue stars. Why is it so? It's just a consequence of the of Wayne's displacement law, which says that the wavelength at peak emission is inversely proportional to the temperature of the black body. And in this case, you can see when you decrease the temperature, the wavelength of the emission increases, and you can see these kind of stars at the maximum wavelength around the red part. Also, you can observe that the lifetime of a particular star depends on where the star is in this diagram. Like if you see a particular star over here, in this particular branch where the temperature is too low and luminosity is also too low, which means the mass is too low. Such small stars, if you look at them, they have a lifetime of around 10 power 11 years. Whereas stars over this part where the luminosity and the temperature is very high, high mass, high luminous, hot stars, they have very less lifetime. Like they immediately turn into these supergiants and might then go become a supernova, and then they just die out in later. Okay, so coming to this giants, you can see that they are really giant in nature. Like the radius of the surface area, you can see that it's really huge, and the luminosity is really huge in this case, but the temperature is low. That's the property. So the temperature is low, but luminosity is comparable to the blue stars. Okay, and these are more interesting objects called white dwarfs. White dwarfs essentially are low luminous stars, and the temperatures also, their temperatures span a lot of region, but particularly they are really in the hot region. And you can see an interesting property here is that the radius is small. So there is this diagonal lines that represent this radius, which is another interesting information here. So you can see this is the radius for one solar radius, and when you go down, the radius decreases. And these are very, very small stars, like that's why they're called white dwarfs, and their radius lies in around 10 power minus 2 solar radius. Okay, let's not dive much into white dwarfs, but if you want, you can check them out. They're really cool stuff to study. Okay, now these are some branches which we can distinguish. Like you have the main sequence, you have subgiants, and of course you have the white dwarfs. Then you have some branches like 1A, 2B, 1B. This indicates the branches where the star essentially blows up as supernova, and these points where you can see giants, they are the giant branch, like this super giants, bright giants, and so on. Now you can observe one thing over here. The axis has changed a bit. Like you can see the axis here was surface temperature, but they've introduced a new thing called the spectral class, and for the luminosity they have introduced something called the absolute magnitude. I just take a while to discuss about what is a spectral class and absolute magnitude, because that will be crucial to understand whatever is coming down. So a spectral class is actually the based on the spectra of the star, like how the spectra looks like. So based on the spectra or the temperature, we can classify the stars into these categories: O, B, A, F, G, K, M. So the stars which are really hot and really luminous, they belong to the O kind of category, where you can see a lot of blue young stars, and whereas the stars in M, K, they are really less luminous stars, and their temperatures are really low, and you can find them in that particular category. That's how you can actually do this classification for different stars and fit them in different categories. Okay, so that's the spectral class. And coming to magnitude, So magnitude is something which you use in astronomy to define the brightness of an object. Like you can, if I say something is, let's say, of magnitude -5 compared to something of magnitude +5, that means the object which has the negative magnitude or the lesser magnitude, not in terms of the absolute value, but just the value in the integer value. If it is lower, that means that particular object is more brighter when you view it from Earth. So that's the concept of magnitude. So more it is towards the negative side, a particular magnitude, the more luminous or the more brighter the object is. And there are two kinds of magnitude called absolute magnitude and apparent magnitude. So absolute magnitude is the magnitude for which you can observe this. If you keep the star at a distance of, let's say, 10 parsec, I mean the star is not at 10 parsec, it's some distance, but let us assume that if you take a star whose absolute magnitude you want to know, keep it at a distance of 10 parsec, and then you calculate the magnitude, which is the normal apparent magnitude, that will be your absolute magnitude. And the absolute magnitude can be related to the luminosity. That is why they are plotting both together, I mean in the same axis. And you will later see that there is a relation between absolute and apparent magnitude, which will be used to find the distance to the cluster or the distance to the object. And the most important thing about HR diagram or ColourMagnitude diagram is that it explains stellar evolution. It explains the concept of stellar evolution or the stellar nuclear synthesis to us. Let's see how does it do that. So this is actually a time step which I took it. I'll give you the link to this because it has a really cool animation which you can go through. So this essentially says that let's say this is the t equal to 0 time for okay. So we are looking at a cluster. First of all, a cluster is like a group of stars, like a cluster of stars, highly speaking. These stars are like they are actually bound together, and they have this the same age throughout, and they are distributed in different ways. Like you can find all you can find all kinds of stars in a given cluster, but the cluster as a whole has particular age. It started at some point, and it's throughout the time it has evolved to a particular stage. That's a star cluster. Okay, so let's observe the HR diagram for a star cluster at t equal to 0. It looks something like this, and most of the stars are in main sequence thing. None of them are in the red giant phase. That means most of them are doing nuclear fusion in their core and producing energy and so on. But after some time, let's say some 10 million years, what happens is that these stars which are really hot, the O type stars, the B type stars, these stars here, the hot stars or the more massive stars, they their fuel, they run out of their hydrogen, and they start to evolve off of the main sequence, and they start moving towards the giant's branch, the red giant branch. Okay, so after around 100 million years, all of the stars, all of the O type of stars have gone supernova, which means they are just completely exploded, and they are in the supernova branch. That's all. Whereas now the B stars, so here there were no B stars involved, whereas here there are B stars which are stripping off the main sequence and moving towards red giant and later supernova phase. Okay, and after 1 billion year, you can see all of the B type of stars have gone towards supernova, and the rest have evolved into red giants. Whereas the A stars, which comes after B, O, B, A, the A stars are now starting to evolve off the main sequence. That's called the main sequence turn off, the point where the stars like A type of stars, they start moving towards the red giant bands. That's exactly the point called the main sequence turn off. Okay, then the G, it follows with the G type of stars. They also start moving towards the red giant branch, and more you'll be seeing more and more red giants popping up during this time. So if you take a cluster of an age around 5 billion years, around 10 power 9 years old star cluster, then you can see this kind of HR diagram, because they will have the stars till G or till A being evolved off of the main sequence, and the HR diagram will look something like this. Whereas if you take younger clusters, like most of the young clusters are open clusters, you can see those kind of form this HR diagram, which doesn't have much population in the red giant and the supernova branch. Okay, so that's your point of main sequence turn off, and more red giants have been populating in your HR diagram. Now after 10 power 10, or sorry, after 10 power 10 years or 10 billion years, you can see all of the O, B, A, F, G stars are all missing from the main sequence, and the red giant branch is really well populated, and there are very less stars in this branch. That means it's a really old cluster, and you will actually see this horizontal branch, which if you remember you have seen over here, which are the supergiants. Also you will be seeing the white dwarfs batch, because they are actually the product which is after the supernova. So after the supernova, the stars come and populate here in the white dwarfs phase. So you will be also seeing the white dwarfs in this case. Yeah, so this is how they look like, right? Okay, I have a video which I hope I can record, or I'll put the link in the description. You can watch this later. This actually shows how stars evolve in an HR diagram. So yeah, you can see how they evolve. So they're putting them in the HR diagram. So this is the current scenario where you have more of the brighter objects, and after 1 billion years it looks something like this. Then you can observe the way it evolves towards red giant branch, and you can see how the turn off happens, how the main sequence turn off is happening here. Okay, yeah, so this is essentially it. So yeah, you can go through this animation later, right? Now coming to color magnitude diagram, I said that color magnitude diagram and HR diagram are equivalently the same. Let's see why. So as I was saying, observers can't directly measure the luminosities and the absolute temperatures. Instead, we like to quantify it using the color and the magnitude, and we also already saw that the magnitude was related to the luminosity and the color is related to the temperature. If you go back a bit, if you just recap what I was discussing about the spectral class, you can see how color determines the temperature. For example, if you find the so if you calculate the value of a particular star using a filter in this particular spectral using this particular filter in the M region, and then using O region, and then you subtract for a star in the M, you will see that M minus O is a positive number, which means that star is more reddish in nature, and so on. So that's how color determines the temperature. The more reddish a star is, the less temperature it has. So color gives you temperature, and the luminosity is directly given from the magnitude or the absolute magnitude which you can measure. So if you measure the magnitudes, let's say using two different filters. Why have been using filters? Because here I am using two filters, let's say R and G. Let's just assume that R denotes the red part of the electromagnetic spectra, whereas the G denotes the green part of the electromagnetic spectrum. Now if you subtract G minus R, so you place a G filter, you measure the values. You place an R filter, you measure the values for a particular star cluster. And then you subtract G minus R. If G minus R is a really positive number, like around 2.5, And if G minus R is a negative number, that means G dominates over R and it shifts towards the green side. Whereas if the G minus R is of a more negative value, that means it shifts more towards R. But actually here G is not referring to green, it's some other wavelength, but you can assume that in this case it's actually the positive side indicates that the temperature is low there and the temperature is high in this side. Okay, I'll come to a more practical example when we are actually analyzing the data. So okay, and finally this is an important thing called the distance modulus. We know that the luminosity follows this inverse square law, which luminosity is f by 4 pi r square. That is, if you go like r more away from the object, the flux received there will be 1 by r square times smaller than what you are receiving at some point near the star. So using that, you can actually determine this concept of distance modulus. This m is the apparent magnitude, which is related to the flux which you measure from Earth. Capital M was the absolute magnitude which I was talking about for a distance of 10 parsec. If you keep a particular star and you measure the magnitude, what is that magnitude? That is the apparent magnitude. Whereas the absolute magnitude, I'm sorry, I messed it up. The absolute magnitude was actually for the star which you keep it at a distance of 10 parsec and then you measure the magnitude. That's absolute magnitude, whereas the apparent magnitude is for the magnitude which you measure for a star directly from Earth, and you can get this distance modulus. M minus m is 5 log 10 d by 10 parsecs. So if you know the distance to that particular star cluster in parsecs, I can find this. Or if I know the distance modulus, which is m minus m, I can find the distance using this equation. Okay, now let's get into some of the good stuff, which is the data part where we are going to analyze various data. So first of all, I need to discuss what is an isochrone, because we are essentially dealing with isochrones in our exercise. We'll use isochrones to verify some of the features which we were discussing earlier. So what exactly is an isochrone? So we saw that in the case of stellar evolution, HR diagram helps us explain the stellar evolution. So isochrone is actually a curve in the HR diagram which represents a population of stars of the same age, of the constant age. Like if you take for example, let's just take this particular example where this is a cluster of some age 10 power 10 billion years. So this is actually an isochrone because it's for this particular age. But if you go to a different age around 10 power 9, this is how the curve look like. So this is actually the isochrone for this particular age. For each age you get a corresponding isochrone. So that's the idea of it. Okay. So isochrones are not just dependent on the age, it's also dependent on another property called metallicity. Metallicity is a property for of the stars which actually denotes the amount of metal it has, or it actually it's related to the way nuclear reaction happens inside the core. So metallicity also plays an important role. So I have to generate isochrones in my exercise. I've already generated them using this particular link, this isochrone generator. You can play around with it. Like you can give some initial age and the final age and the step size also for the metallicity, and you will be getting the isochrones. The isochrones will be available in the repository. One of the data set looks something like this. So this is an isochrone for this particular metallicity of 0.00004. These are the columns. There is a age column, there is a initial mass for the stars, then this is, I think this is the increment of the mass, and then this is the luminosity, this is the temperature column. These are the most important columns like mu, mp, mv. So these are the magnitudes in different filters. Like this is a U filter, This is NB filter. Don't worry about the letterings like UB if you don't know about them. These are actually standard astronomy filter numbering, filter um, standards called photometric standards. You can look up the wavelengths associated with that. So B, V, and so on. And yeah, so that's essentially it. So if I find this temperatures and the luminosities for a particular these are actually codes which numerically run through the stellar evolution and find out the stars in the clusters, like the age of the stars and so on. So let's actually try to plot and see. So you can see that this particular data which I took for 0.008, I'm using 0004 for the reference, but both are the same. You can see the first column was age, and 1, 2, 3. The third 0, 1, 2, 3. The third column was luminosity, and the fourth column was the temperature. So I take the 0, 3, 4. If you remember, this np.load text was the command which I used for loading the text files into different numpy arrays. I use the unpack equal to true because I want them to be unpacked. I'm using as the column 0, 3, and 4. Okay. So this is actually this isochron was generated throughout the evolution of the stellar cluster. So if you remember, the star cluster evolved from something like this to something like this. Okay. So each of these snapshots at each age or at each epoch is an isochron, right? So I can actually plot all the isochrons for different age and see how does that look like. So I'm finding out the array indexes where the age is equal to these values. For example, this is corresponding to an age of 10 power 7, that is 10 million years. This is some 100 million years, 1 billion years, and so on. So I'm finding those numpy array indexes, using those indexes, because if you see, like if this is a particular age 6.60, then for this particular age I have so many entries with so many luminosities and temperatures which I can plot and generate an isochron. So I use the indexing, and then using the indexes I generate the isochron by just plotting it here. So this is just the plotting code where I plotted for 10 million years, which the curve looks something like that. I'll actually zoom in. Yeah. So for 10 million years, you get a curve which goes something like this. For 100 million year, which is over the green, something like this. The 31.6 of course will be this one, is 316.2, and this is the 1 billion. You can see how they all look like. I mean, they are this particular guy essentially means that all of the odd type of stars have been moving towards the giant phase, whereas here you can see O, B, and all are moving. If you come to this, you can see it's very similar to what we were discussing over here, which is something like this, where you have all the O, B, A, F, G stars missing from the main sequence. So I think that's clear now, like how exactly the isochrons are varying. So keep in mind, this is of a metallicity Z equal to 0.008 and for varying distances. Okay. Now immediately your question should be, how does that look? How does the plot look like if you keep the age constant and if you have various clusters of varying metallicity? Let's find that out as well. Again, I'm importing some stuff. I'm importing the B and V values of magnitudes using the text files for different metallicity 008, 0001, 004, and so on. And also I'm finding the age because I want that to plot as well. I'm now plotting for age of around 10 power 8, 100 million years, and see how does that look. So I'm plotting for age of 100 million years, and I'm looking at star clusters of varying metallicity. It looks something like this. You can see how metallicity affects the diagram, but you can observe there how it actually affects the turn off point the of the main sequence as well, which is somewhere over here. Okay, so yeah, I hope this is clear. So we are plotting, by the way, we are plotting B minus V on the x-axis. This is more towards the V side, which is the low temperature, and this is the high temperature side, more wavelength, less wavelength, and this is just the luminosity of the V side. And I'm plotting it for various metallicity and for a constant age of 100 million years. Okay, so yeah, this is about isochrones. Now let's move on to analyze this data which I have in my repository, which is Pleiades star cluster M45. Really beautiful thing to observe using your telescope. Let's actually see what's the age of this cluster. By the way, this is an open cluster. Like, as you can see, the stars are not gravitationally bound enough. If you look at an closed cluster, you will see that they are really close to each other and they are really bound, whereas this is an example of an open cluster. Usually open clusters are young star clusters, global clusters are more old clusters. Okay, so yeah, I am now my aim is to so I have this data file here called m45.dat, which have columns of V and BV, which means I have already calculated B minus V and stored in a column, and I have a column which gives you V. So I take that out. You can look at it later if you want. I can open that and show. Yeah, so this is what it looks like. These are the reference numbers, and this is the V, BV, UB, and I don't want UB. I'll just stick with V and BV, and I take that out using np.load text. Okay, now I am looking at a star cluster age of around 100 million years. So initially this is just a guesswork. My aim is to find the distance and the age to this cluster. Okay, so let's keep a 100 million years of age and see what does it look like. So I'm plotting for various metallicities for an age of around 100 million years. Looks something like this. So this is this pink guy, this pink isochrone is actually the data, the color magnitude diagram of Pleiades of M45, whereas these are the isochrones which you generated. You can obviously see there is a difference. Now you can see the pattern is somewhat same, only that it's shifted a bit. I mean, you can see each and every point coinciding with this. If you actually shift this guy a little bit down, keep in mind here I am plotting the apparent magnitude, and this is the apparent magnitude, and this is the absolute magnitude which I am observing, whereas this is something which you generate using a code, using a numerical code, whereas this is something which you observe. Okay, now if you go back to your formula for distance modulus, you can see that m minus m, where is it? You can see m minus m is 5 times log 10 d to the base 10, which means if I know this distance modulus m minus m, I can actually find the distance. So distance modulus is nothing but a shift in the isochrones or a shift in the color magnitude diagram. Keep in mind, this is the capital M's, and this is a small m. So the absolute value of this will actually give you, absolute value of this shift will actually give you the distance to the star cluster, which we'll find out soon. Okay, so I can observe some things. I can throw away some of the metallicities, like these guys over here, 0.001, 0.004, and so on. 0.0019, the purplish violet thing. I just throw them off and see how they look like, and I'm plotting it now without scatter. I'm just simply plotting it. Can actually see some similarities here, but I'll also have to look at how does this change if I change the age. Now I go back and I change the age to something around 10 power 8.2, or the log of age is around 8.2, and then observe how does that look like. And you can see it looks something like this, and you can compare with this. There is a series off here, whereas over here you can see more and more it's coming closer to what is being represented here, which is the really good news. And so I can keep my age around here, which is fine. Now I'll further I can do another trick. I'll shift it now using a number. So I have already worked out this by myself. You have to try it by yourself. You can try different numbers of shifting. So here I'm shifting it with some 5.2. Actually I shifted it with various numbers, and I found that around 5.2 you observe something like this. Okay, now I shifted furthermore 5.6, and this time I am neglecting one guy, which is your 0.004, which is really off putting. I just ignore them, keep my values between 0.04 and 0.03, which is fine, which is a really good bound. Okay, and this is what I get. So this is for 0.003, this is for 0.004. So I should be changing the title and so on. I'll do that before uploading it to the GitHub. But this is the thing. So you can see that it's actually very well coinciding with the 0.03. Not exactly. There is a bit different. So I can actually say that the metallicity, I'll just comment it over here. So I can observe observations. So first observation is that the metallicity should be around let's say, so metallicity is indicated by this guy Fe by H. Okay, let's say it's around 0.03. I'm keeping bounds, and 0.04. Second observation is that I shifted by a distance modulus of 5.6 here, which is, again, I'm not doing a perfect scientific calculation. I have to count in for errors and so on, but this is a really basic way of doing this problem, doing this exercise. Okay, distance modulus, let's say 5.6. okay, and then the next observation is, okay, about the age. The age was around 8.2. so log age base 10, 8.2, which means the age of the cluster is around 10 power 8.2. These are the observations which you get. So if you want to play around with more data, which is not exactly playlist, you can actually do this. So this is the link for generating isochrones. You might it will take some time for you to settle up with this environment where you generate stuff. For the data for clusters, I have given you some links here, but the best one is SDSS. One second, I'll open that link. Let's pause. Right, so this is the link for SDSS Sky server. SDSS is I think I already discussed about SDSS previously, but it's a really good place where you can get a lot of publicly available astronomical data, and you can look at various objects. If you give the name or the details of it, it will generate you the data. Okay, I'm not able to do this. So okay, if you're not able to get the result correct, you can actually type in the RA and declination here. and then you can search it, but it should come. Mm, okay, that's not working. Okay, I'll just leave the link. You can work this out. Also, I'll leave another link in the description about other ways of getting this data. I use STSS, whereas you can. So this is another link where you have all the essential clusters, list of essential globular clusters, or other link is for open cluster. For example, this guy. If you take a cluster like this, you go to the link of that particular sky STSS column. If you observe, you can get all the data out and you can then work with it. Okay. um, you can also use a query to do this, but I'm not discussing that for now. But if you want me to discuss, keep a session on uh, querying SDSS and databases, just let me know in the comments. Okay, I think that's it for this particular session. So we learned about the star clusters, the theory of star evolution, and how isochrones play a really important role in finding the age and the distance to a particular star. Again, this is the really basic method. People are working on various new innovative methods to come up with better and better way to fit isochrones, to generate isochrones and to find the ages of clusters and so. Okay, yeah, that's it for this one. Next time we'll discuss more interesting concepts in astronomy through Python. All right, bye.